Good afternoon again. It's Evan Snyman from Umkhuluko, Making a Difference. We're looking at the third video in the calculus series. This time we'll be looking at first principles. So what we looked at last time is the movement of notation for the gradient m, for average gradient. Okay, for average gradient, from being the gradient was the change in y over the change in x, which was y2 minus y1 over x2 minus x1, to being f of a minus f of b to over a minus b, importantly, to now being f of a plus h minus f of a over h. And the key here again was that this was no longer two terms. So here we had two terms in the denominator. Here we had two terms in the denominator. But now we had a monomial in the denominator. Again, we are talking about here the gradient over 2 points, such that, again, if we say similar drawings to what I've been drawing up till now, we're talking about the gradient over 2 points, such that we had something like that. And if we're talking about these 2 points, we're talking about the gradient across these 2 points. And again, for the sake of the last one's notation, this was a with f of a, and this value here wasn't a value, and that was the key concept. We said that this difference was going to be h, such that this point was now a plus h, which meant that the y value that went with it was f of a plus h. Okay, so again, we've got the 2 points, and we talk about the average gradient across those 2 points. But what we talked about as well in this idea of the limit was what would happen if we now took the idea of the same picture again, drawn again. What would happen if we took this second point, or this h value, this distance here h, and we made it as small as we could? Now, what I want you to imagine is a car that I used to have, whose speedometer, the measuring device that told me about the speed of the car, that the speedometer was inaccurate. The speedometer told me what was happening about 3 or 4 seconds earlier. So when I accelerated, it stayed 0, and then slowly but surely rose to catch up to my idea, okay, to my speed, okay, and it was quite difficult to gauge your actual speed when you're driving, because the speedometer was always behind time. So again, what I'm asking you is, what if I made this idea of this distance between these two things, this h, as small as possible? In other words, it would be a much better average, it would be a much more useful gauge of value if, instead of having f of a plus h, I was now looking at something where this h value was getting smaller and smaller and smaller. So if I did that, what I'm now looking at is a much better idea of an instantaneous gradient. So what is happening at the instant? Now, if you think about your parents' car or any car that you might be familiar with, most car speedometers are telling you what's happening at that very moment. Okay, so an instantaneous gradient, no longer looking at the idea of an average gradient. And so this idea of an average gradient, we are trying to put to pasture, we are trying to put to bed, we're trying to get rid of this idea, and we are now trying to find the idea of an instantaneous gradient. And so what we're going to do for that is we're going to say, let's consider what would happen if we made the limit as h tended to naught. Now remember, we are not saying that h is naught, of f of a plus h minus f of a over h. Now remember, what would happen if we made h naught? So if we made h equal to naught, we would get f of a minus f of a over naught, which would be naught over naught, which we said is this really weird thing that's not even undefined. So we really are flirting with danger here. So we are saying that it is tending to naught. We are not letting it equal naught. Okay? We are tending to 0. We are not allowing it to equal naught. And so what I'm going to look at now is a simple numerical example, and then I'll expand it into algebraic examples, and we'll look and see if we can't find some shortcuts to help the process. So what I'm going to look at for today is this limit as h tends to naught of f of a plus h minus f of a over h. And this is what I want to play around with. So what I'm going to look at today is the function f of x equals, let's go with 3x squared minus 2x plus 5. Why not? And we want to find out what's going to happen at the gradient. Again, I know I'm not specifying whether it's instantaneous or average at this point in time. The gradient at x equals 2. So what I'm going to look at, okay, is the gradient at x equals 2. So f of 2 equals 3 times 2 squared minus 2 times 2 plus 5. So we know that the y value over here is going to equal 12 minus 4 is 8 plus 5 is 13. So it's going to the point 2 and 13. And I'm going to consider what happens if we add an h to this. So we can have a quick discussion, just do some algebra. 2 plus h would be 3 times 2 plus h squared minus 2 times 2 plus h plus 5. We need to do some work. It's going to be a bit messy. We're going to get 3 times 4 plus 4h plus h squared minus 4 minus 2h plus 5. And we're going to get a final answer, which is, as I said, quite messy, but not a final answer yet, plus 12h plus 3h squared minus 2h plus 1. I've put the 4 and 5 together so long. So I'm going to get an answer of 3h squared. And that would be the y value if we needed it. It would be 3h squared plus 10h plus 13. Okay. Cool. So what we're going to look at now is what happens if I was to take this now and to look at the gradient across that point. So the limit as h tends to naught of f of 2 plus h minus f of 2 all over h would equal the limit, again, notice where the notation lies, it's on the right-hand side of the equal sign, of 3h squared plus 10h plus 13 minus the, where are we now? Minus the 13 that we had on the other one, which would give us all over h. We don't have h equaling naught yet. We can see that the 13s will cancel at the top. So these 13s are going to cancel. Again, when we talked about how to deal with the limit, we said we want to factorize. And what I'd like to see here is that the h's are presenting as a common factor. So I'm going to have h as a common factor. and you can hopefully see what's going to happen with my denominator. My problem is going to go away. Okay, my problem denominator of h is going to go away. So I've got 3h plus 10. Okay, sorry about that. I'm just going to erase that and make it a little bit neater. Okay, and so when I do so, I've got 3h plus 10. Again, we look at this a bit further. The h's are cancelled because that's why we did the factorizing, to make the problem go away. So the problem went away. And what we got here was equals the limit as h tends to naught of 3h plus 10. Now, there's no reason at this point that the h can't become 10, sorry, that h can't become 0. So I'm now going to have equals 3 times naught plus 10. I'm simply going to substitute. And so what I get is 10. Now, this 10 is going to be the gradient at x equals 2, but is the actual gradient at that point. Okay, we have made the distance between these 2 points actually 0. We've actually brought those 2 points so close together with one another that we actually are dealing with a single point. And so now what we have is not an average gradient, but what we actually now have is an instantaneous gradient at 2. So now what we actually have is what we are from now on going to use the word gradient. But whereas in the previous chapters when we said gradient, we meant average gradient, from now on in matric, when we talk about gradient, unless we specify that we want to find the average gradient, we are now talking about the instantaneous gradient. So this is the gradient at 2. This is the instantaneous gradient at x equals 2. Okay, and so we have now been able to find the gradient at a single point. And again, I just want to go back up to the top. For that function, f of x equals 3x squared minus 2x plus 5, the actual gradient at a single point is, at the point x equals 2, the single point, is now actually the instantaneous gradient. It is no longer the average gradient. It is now instantaneous gradient. Now, some of you people may have found this method to be a little bit tedious. And so what we're now realizing is that actually the instantaneous gradient is given by this, we can use this shortcut to find the instantaneous gradient. Now, this method is quite tedious. And so what we're going to do is we're going to realize that we only have to do it once or twice in our lifetime. That's the good news. We will hopefully find a shortcut fairly soon. And what we are just seeing now is that the instantaneous gradient is the limit as h tends to naught, again, of f of x plus h minus f of x all over h. And this formula you'll see on your formula sheet, and you'll see it tons and tons of times again. This formula is very, very important. Now, the good news is that this long-winded way of solving it is what we call first principles. And I will do it today for you. You will learn to do it off by heart, and then you will never do it again unless they specify do the sum by first principles. And so the good news is we do not need to do this every single time. You need to do it once in possibly in an exam, and we'll look at it to try and find a shortcut that will be a lot more effective at the moment. So because this function is called f of x, and m is the average gradient. So remember, m was an average gradient. M was the average gradient. We can't use M anymore, okay? So if M was the average gradient, we are going to replace it with a new notation that says F dash. And F dash is the instantaneous gradient. Okay? So we're going to call this thing F dash of X. Okay? And we're going to say that because it came from that other function F of X, we're going to say that it was derived. Okay? So we're going to say it is derived from that. Okay? And another way of saying it is because of this minus sign over here, we also sometimes use the word to differentiate. So the instructions here are to derive or to differentiate. Okay? To derive or to differentiate means to find the average gradient from a given function. We can do that hopefully by a shortcut, as I keep saying, but we would like to find it by first principles. Now, I'm going to do one or two more with you and show you that we can get there using, hopefully we can work out the shortcut without me giving it to you. Maybe you can find it without, on your own. So I want to derive f of x equals ax cubed by first principles. That's the instruction. Okay, so I know f prime, okay, that's what that little dash is called, f prime equals the limit as h tends to naught of f of x plus h minus f of x all over h equals the limit as h tends to naught of a x plus h cubed minus ax cubed all over h equals, now I'm going to unfortunately need to be fairly quick here, so I'm going to expand quite quickly. Ax cubed plus 3x squared h plus 3x h squared plus h cubed minus ax cubed all over long divide line h. Again, same as in the previous one, hopefully you can see that the ax cubed and the ax cubed will disappear, that the other three terms all have an h involved as a common factor. Okay, so they all have h's as a common factor. And we saw in the previous example how that solved my problem of the h in the denominator. So what I'm now going to have is that this equals the limit as h tends to naught of taking out the green h as a common factor. I'm going to have 3x squared plus 3xh, 3xh plus h squared all over h. Again, the reason we did this, take out the common factor, was so that the h's would cancel. I have removed my problem, but I'm going to just take an extra step here so we can look at it. It is the limit as h tends to 0 of 3x, how about they went for loops, so let's tidy that up. 3x squared plus 3xh plus h squared. And now that I no longer have a problem, I can substitute in the naught, and I'm going to get equals 3x squared. So I've now gone and applied the limit by substitution. Okay, so again, notice how the notation has gone away. Okay, because I have gone and applied the limit. Okay, so what I'd like to do quickly is I'd like to just keep track of the sums that I've done. And so what we saw here just now was when I had f of x equaled 3x squared minus 2x plus 5. We had an answer just now of 6x minus 2 as being f prime of x. When we had f of x equals ax cubed, we had an answer of 3ax squared. I'm going to do one more. Okay, and so let's have a look at what happens if f of x equals a over x. I'm going to derive it by first principles. So again, f prime of x equals limit as h tends to 0 of f of x plus h minus f of x all over h. In this case, it's going to be the limit as h tends to 0 of a over x plus h minus a over x, all of this over h. Okay, I'm going to choose to do two things with it. I'm going to choose to bring this h out to the side. And as with all things when you add fractions, I'm going to look at an LCD over there. So I've got the limit as h tends to 0 of the common denominator here would be x plus h times the x. So it is ax minus a x plus h. And I'm dividing that by h, which you guys know is the same thing as multiplying by 1 over x, 1 over h. So I'm going to multiply this thing by 1 over h. I now have the limit as h tends to 0. Well, I'm going to have the following happen. So let's have a look. I'll just put this in neatly. Okay, so let's have a look what's going to happen. I've got my denominator, x times x plus h. I am timesing by 1 over h. And here I've got ax minus ax minus ah. And these two terms are going to cancel. And so what I now have is an answer of, or the next line of equals the limit as h tends to 0 of minus ah. So, yes. Yes, sorry, thing x plus h times 1 over h. These h's, as we've described before, will cancel. Okay, and again, what I'm left with is an answer, is a situation where I've got the limit as h tends to 0 of minus a over x plus h. For what I hope you notice is that by making that, getting rid of that h that cancelled, I've actually removed a problem because h can now actually, I can now actually apply the limit and make the other h naught, because making h naught no longer makes the denominator 0 and therefore undefined. So I can now apply the limit. Okay, and to apply the limit, what I'm going to do is going to make h naught. So I've got minus a over x times x, which is minus a over x squared. Now I'm going to quickly go back to that previous table where I was trying to keep track of things. So when I had a over x, the answer was minus a over x squared. Now it might not be so clear to see in that example, but what if I chose to write this as being ax to the minus 1, and I chose to write it in what we call polynomial form. Okay, so what if I wrote it in polynomial form? In other words, I removed the denominator and I wrote the denominator instead as an exponent. Well, then this version would become minus ax to the minus 2. And maybe if you look at how these things interact, especially these two, okay, especially these two, you might be able to see the shortcut. And the shortcut, again, let's give it to you as we close this video so we can use it in the next video. The shortcut says if f of x equals ax to the power of n, then its derivative is an x to the power of n minus 1. What we do is we bring the power to the front, as you can see over there, step 1, and then we drop the power by 1, as you can see at the top here, and that is step number 2. Please just confirm this. Ax cubed, we bring the power to the front, and we drop the power by 1. There we go. And when we write in polynomial form, when we take the power to the front, we get minus a. And careful, when we drop the power by 1, minus 1 lowered by 1 is actually minus 2. Okay, so there we go with first principles. Please remember, there will be one question on first principles in the paper. There's always a bookwork question. That is the end of lesson number 3.